Welcome to another episode. I'm glad you're here. Wherever you are, lying in bed, closing your eyes, or simply letting the noise of the day settle into quiet, this is your time to rest, to listen, to drift with a story. If you'd like, share in the comments where you're listening from and what time it is there. It's always fascinating to see how one story can reach so many places at once. And if you enjoy these journeys, I invite you to subscribe so you'll always have another calm space to return to. Tonight, we're going to follow something simple, something almost too ordinary to notice. A pendulum. Just a weight, swinging back and forth. Yet, hidden in that gentle motion are discoveries that changed our understanding of time, of motion, even of Earth itself. From Galileo's quiet wonder beneath the chandeliers of Pisa's cathedral, to Foucault's great pendulum revealing the turning of our planet, this simple swing has told us truths that stretch from the human heartbeat to the movement of the stars. So, let yourself settle as we trace the hidden life of pendulums. The story begins in a cathedral. It is the late 16th century, and a young man named Galileo Galilei has entered the grand interior of Pisa's cathedral. The air is filled with incense, the murmurs of prayer, and the flickering of candlelight against marble columns. But Galileo is not looking at the altar, nor at the icons. His gaze is drawn upward. From the high ceiling, enormous bronze chandeliers sway gently, disturbed by the draft of opened doors or the subtle vibrations of footsteps below. To most people, the swinging of these lamps is nothing unusual. But Galileo notices something peculiar. He times their motion, not with a clock, for such precision instruments hardly exist yet, but with the rhythm of his own pulse. Placing 2 fingers on his wrist, he measures the beat of his heart against the swing of the chandeliers. And what he finds astonishes him. No matter how wide the arc, the time it takes for a lamp to swing from one side to the other seems nearly the same. A broad, sweeping swing and a small, gentle swing appear to take an equal amount of time. This principle would later be called isochronism, meaning equal time. To Galileo, it must have felt like discovering that the universe had hidden a secret in plain sight. For centuries, humans had watched pendulums without ever truly seeing them. The rocking of a cradle, the swinging of a bell, the hanging weight of a plumb line used by masons. All were familiar motions. But Galileo's gift was not merely observation, it was curiosity paired with persistence. He asked questions where others accepted ordinary patterns. Could it really be that a pendulum, left to swing, marked time as faithfully as the beat of a heart? In 1583, Galileo was only 19 years old. He had just begun his studies in medicine at the University of Pisa, pushed by his father to pursue a respectable profession. But already his mind was wandering beyond the body to the wider mechanics of the natural world. The chandelier in the cathedral was a revelation. What had begun as an idle glance during a church service would become the seed of a lifelong fascination with motion, mechanics, and ultimately the laws that govern the cosmos. Galileo began to experiment. Without a stopwatch or a laboratory, his tools were simple: string, weights, and his own pulse as a metronome. He suspended small lead bobs from cords of varying lengths and set them swinging. He counted heartbeats, listened carefully, and compared. The discovery seemed to hold. A pendulum's swing was not dictated by the size of its arc, but primarily by the length of the string. This insight was profound. Timekeeping in Galileo's day was notoriously imprecise. Sundials told time only under clear skies. Water clocks dripped steadily, but were prone to freezing or clogging. Mechanical clocks existed but were wildly inaccurate, often wandering by 15 minutes or more in a single day. In an era when navigation, astronomy, and the organization of civic life all cried out for precision, the pendulum offered hope of an entirely new standard. Galileo did not yet know the mathematics that would one day explain his observation. That would come later, through the work of Christian Huygens and the blossoming of classical mechanics. But even without equations, Galileo understood the pendulum's promise: a natural, regular, almost incorruptible rhythm. Imagine him, in the quiet of his workshop, releasing a weight tied to a string and watching its back-and-forth journey. In that hypnotic swing, he could glimpse something beyond the reach of ordinary timepieces, a mechanism that might one day allow clocks to tick with an accuracy never before achieved. It is worth pausing to consider what it means to discover such a principle in the late Renaissance. Today, we are used to precision. We carry digital watches that lose less than a second in a year. We measure time with atomic transitions that would take millions of years to drift by a heartbeat. But in Galileo's Pisa, the very concept of seconds was fragile. Ordinary citizens marked time by church bells or the sun's passage. Even scientists could not easily compare results across continents because no two clocks agreed. In that environment, the pendulum was not just a curiosity, it was a revelation. Galileo pushed the idea further. He began timing not only his pulse, but also songs. By singing a note or humming a steady rhythm, he could create a kind of auditory ruler to compare the swing of different pendulums. This interplay of music and mechanics came naturally to him. His father, Vincenzo Galilei, was a musician and music theorist who had written about the mathematical relationships of tones and harmonics. Galileo grew up in a household where measurement and proportion were discussed as part of art itself. The swing of a pendulum, steady and rhythmic, was not unlike the beat of a drum or the plucking of a lute string. By 1602, Galileo had refined his studies. He realized that while the pendulum's period was nearly constant for small swings, it was not perfectly so for larger ones. Still, within the practical limits of observation, the error was small enough that a pendulum could be trusted as a regulator. His notes describe experiments where he compared pendulums of different lengths, discovering that the time of each swing was determined not by the weight of the bob, but by the string's length. A heavier mass did not swing faster or slower than a lighter one of equal length. This too was a revelation, breaking from Aristotelian notions that heavier bodies behaved differently in motion. The pendulum, in Galileo's eyes, was a laboratory of nature's secrets. It demonstrated that motion followed laws discoverable, repeatable, and universal. This was not mere philosophy, it was a tangible, swinging proof. One of Galileo's most ambitious ideas was to design a pendulum clock. If each swing could be trusted to mark nearly the same amount of time, then attaching a pendulum to the gearing of a clock might yield an instrument of unprecedented precision. Around 1637, near the end of his life, Galileo and his son Vincenzo sketched plans for such a clock. It was a bold vision, a machine where the steady arc of a pendulum governed the turning of hands across a dial. Sadly, Galileo would never see this dream realized. His declining health and eventual blindness prevented him from constructing the clock himself. The design remained incomplete, but his insight did not fade. Decades later, Christian Huygens in the Netherlands would take up the challenge and build the first true pendulum clock in 1656. That invention would revolutionize timekeeping, shrinking daily error from a quarter of an hour to mere seconds. And it all began with Galileo, gazing at a swinging chandelier. It is tempting to imagine the moment as poetic destiny, a young student, distracted in a cathedral, stumbling on a principle that would alter science. But Galileo's genius was not accident alone. His observations of the pendulum fit into a lifetime of challenging established wisdom. He tested falling bodies by dropping weights from the leaning tower of Pisa, rolled balls down inclined planes to study acceleration, and turned telescopes toward the heavens to reveal moons around Jupiter. The pendulum was one note in a symphony of challenges to tradition, each swing marking a beat in the slow march from medieval thought to modern physics. The cathedral chandelier has become legendary, told and retold in science histories. Some scholars debate whether Galileo truly made the observation in the dramatic way later recounted, or whether the story was polished with hindsight. But the essence is undeniable. Galileo grasped the pendulum's potential when few others did. He saw not a decoration but a tool, not an ornament of worship but an instrument of truth, and the implications were immense. Consider navigation at sea. By the 17th century, European powers were sending ships across vast oceans, but sailors lacked accurate ways to determine longitude. The difference of a few minutes of timekeeping could translate into hundreds of miles of error. Pendulum clocks, though initially too sensitive to the rocking of ships, offered the first glimpse of a solution, the promise of precise time across the world. In the quiet swing of a lamp, Galileo had uncovered a principle that would one day guide explorers across oceans, astronomers across the sky, and scientists across centuries. His idea of the pendulum as a clock was not realized in his lifetime, but the seed was planted, and like the steady arc of a pendulum itself, that seed would return again and again, swinging back into human history whenever precision and truth were needed. Galileo's pendulum experiments also fed into a deeper philosophical shift. For Aristotle and the scholastic tradition, motion was often described qualitatively. Heavy things fall because they are heavy. Light things rise because they are light. Galileo's careful counting of swings broke that mold. He insisted that nature could be measured, not merely described. A swinging pendulum was not just a metaphor for regularity. It was an actual ruler, a natural clock set into motion by gravity. In that sense, Galileo's observation was as much philosophical as it was scientific. It declared that the universe runs on laws that can be discovered, tested, and trusted. Think of the courage that required. In Galileo's day, to challenge Aristotle was to challenge centuries of authority. To claim that time itself could be measured more faithfully by a swinging weight than by the heavens or the traditions of scholars was radical. Yet Galileo persisted. He did not simply watch. He experimented, repeated, tested, and believed that truth lay not in doctrine, but in evidence. And so, the pendulum became part of the foundation of modern science. A small observation, a young man's curiosity, and a chandelier in a cathedral combined to alter our relationship with time forever. The cathedral lamp that caught Galileo's eye was only the beginning. The principle of the pendulum, its steady, dependable rhythm, would wait several decades before being transformed into a practical machine. That step came not in Italy, but in the Netherlands, through the mind of Christian Huygens. Huygens was born in 1629 in The Hague into a wealthy and influential family. His father, Constantine Huygens, was a diplomat and poet who moved in the circles of princes and scholars. Young Christian grew up surrounded by culture and ideas, with access to education and connections that allowed his talents to flourish. From an early age, he displayed remarkable aptitude in mathematics and mechanics. By his mid-20s, he was already making discoveries in optics and astronomy, and would later go on to discover the true nature of Saturn's rings and identify its moon Titan. But it was in 1656, at the age of 27, that he achieved a breakthrough that would alter daily life for centuries: the pendulum clock. To understand the magnitude of this achievement, one must picture timekeeping in the mid-17th century. Mechanical clocks did exist, gears, weights, and escapements ticking away in towers and homes, but they were woefully inaccurate by modern standards. A typical clock might lose or gain 15 minutes in a day. For most people, this was acceptable. After all, they relied on church bells, sunrise, and the rough division of the day into morning, noon, and evening. But for astronomers charting the skies, or navigators steering ships across oceans, such imprecision was crippling. A few minutes' error in tracking the heavens could throw off star charts. A few minutes lost at sea could mean missing one's intended landfall by hundreds of miles. Huygens saw in Galileo's pendulum principle the key to solving this. The pendulum, with its nearly constant period, could act as a regulator, controlling the release of a clock's gears with reliable rhythm. Previous escapement mechanisms allowed clocks to tick erratically, at the mercy of friction and uneven power from falling weights. A pendulum, however, imposed its own law, a steady beat, unaffected by the driving force. By coupling a pendulum to a gear train, Huygens created the first clock that could keep time with astonishing precision, accurate to within less than a minute per day, and soon improved to just a few seconds. Imagine the astonishment this must have caused. To people accustomed to clocks that wandered across the hours, a device that stayed faithful day after day was nothing short of miraculous. For the first time, humans could rely on an instrument that divided the day not by approximation, but by certainty. Time itself was being tamed, its wild drift harnessed into a steady rhythm of tick and swing. Huygens' pendulum clock was not merely a technical marvel, it was a cultural shift. In cities where such clocks were installed, the sense of communal time became sharper. Bells could ring at precisely the same moment each day. Civic life, commerce, and worship could synchronize with new regularity. The idea that a day was not just a rough flow of events, but a sequence of measurable, repeatable units, began to seep into consciousness. Humanity's relationship with time was quietly but profoundly altered. Astronomy was one of the great beneficiaries. In the 17th century, Europe was in the midst of a celestial revolution. Telescopes revealed moons circling Jupiter, phases of Venus, spots on the Sun. To make sense of these discoveries, astronomers needed precise timing, to measure the transit of a star across the sky, the eclipse of a moon, the swing of a planet against the constellations. With pendulum clocks, they could now record observations with unprecedented accuracy. Data became sharper, predictions more reliable. The heavens themselves seemed to fall into step with the swing of a weight. Navigation, too, stood on the cusp of transformation. One of the greatest challenges for sailors was determining longitude, their east-west position on the globe. Latitude could be found by the height of the sun or stars, but longitude required knowing the precise time difference between one's current location and a reference point. A clock that kept true time, unaffected by the irregular roll of a ship, was the dream of every navigator. Pendulum clocks at first failed at sea, too delicate to withstand the constant motion, but on land they provided the essential groundwork for mapping coastlines, charting ports, and establishing accurate tables of lunar and solar positions. By the 18th century, marine chronometers would take up the challenge at sea, but they owed their lineage to Huygens' pendulum clocks. Daily life also changed. Households that could afford them began to keep pendulum clocks, first as luxuries, later as essentials. The stately grandfather clock, with its swinging weight visible behind glass, became a symbol of order and reliability. Timekeeping moved from the public square into the private home, reshaping how people thought about their days. No longer tied solely to bells and sunlight, individuals could schedule tasks, meals, and meetings by the steady tick of a machine. The Industrial Revolution that would follow owed much to this new sense of regulated time, as factories, trains, and workers synchronized not by guesswork, but by precision. The ripple effects spread globally. Colonies, ports, and trade routes began to align their schedules. Astronomers in Paris, London, and Leiden could compare data knowing their clocks agreed. Over the centuries, this convergence would grow into the global standardization of time zones and the eventual adoption of coordinated universal time. At the root of it all was the pendulum, a simple weight, swinging back and forth, imposing order on human life. There is a certain poetry in this. For thousands of years, time had been measured by the heavens, the rising of the sun, the passage of stars, the cycle of the moon. With the pendulum clock, time was brought down to earth, tied not to distant celestial bodies, but to the pull of gravity on a swinging weight. In every tick, humanity heard the voice of the planet itself, steady and impartial. Christian Huygens did not stop at his invention. He published his work in a book titled Horologium in 1658, describing the principles of his pendulum clock. Ever the scientist, he continued refining the design, developing solutions to the imperfections Galileo had noted. Among these was the fact that a pendulum's swing was not perfectly isochronous. Wider swings took slightly longer than smaller ones. To correct this, Huygens introduced the idea of a cycloidal pendulum, shaping the path of the swing to achieve greater regularity. Though complex in practice, it revealed his deep commitment to perfecting the science of time. The influence of Huygens' invention spread rapidly. By the late 17th century, pendulum clocks were being built across Europe. They adorned churches, town halls, and observatories. Their tall cases and solemn ticking became part of the rhythm of daily life. Some were marvels of craftsmanship, with intricate woodwork and gilded faces. Others were austere and functional, but all shared the same beating heart, a pendulum enforcing regularity, swing after swing. It is worth pausing to consider what this did to human psychology. Before the pendulum clock, time was a fluid experience. Days stretched or shrank with the seasons, tasks were completed when they were finished, and meetings occurred roughly around noon. With accurate clocks, a new discipline emerged. Appointments could be fixed to the minute. Work could be divided into exact shifts. Even leisure began to be measured. Time became not just a backdrop, but a ruler, carving life into measurable segments. The swing of a pendulum had changed not only science, but culture itself. The pendulum clock also underscored a philosophical truth that Galileo had glimpsed. Nature operates with laws that can be harnessed. In every identical swing, people saw evidence that the universe was not chaotic, but orderly. Gravity, motion, and rhythm worked together in harmony. A pendulum was more than a machine part. It was a visible symbol of lawfulness, a daily reminder that the world could be understood and predicted. By the 18th century, pendulum clocks had achieved remarkable precision. Improvements in design, better escapements, temperature compensation, and craftsmanship brought their accuracy to within a few seconds per day. Some observatory clocks, carefully maintained, erred by less than 1 second over weeks. For the first time, humanity could measure time with a fidelity that rivaled the stars themselves. In fact, for centuries, pendulum clocks served as the ultimate reference against which astronomical phenomena were timed, and later against which new technologies like quartz oscillators were judged. The global standardization of time owes much to this era. As pendulum clocks proliferated, nations and cities could align themselves with shared references. Observatories like Greenwich became centers of precision, their pendulum clocks defining the meridians of the world. Railways, when they came, depended utterly on synchronized clocks to prevent disaster. Telegraph networks transmitted time signals across continents. The planet itself seemed to fall into rhythm with pendulums swinging in glass cases. In retrospect, Huygens' invention appears inevitable. Galileo had glimpsed the principle, and the world longed for precision. But inventions are never simply inevitable. They require imagination, persistence, and the willingness to trust a simple idea against centuries of tradition. Huygens provided that, and in doing so, altered human life at every scale, from the astronomer's observatory to the sailor's voyage, from the city bell tower to the family living room. The pendulum clock is more than an artifact of history. Even now, when atomic clocks measure time by the vibration of cesium atoms and satellites beam signals to our phones, pendulum clocks remain symbols of trustworthiness and order. They are reminders that accuracy was once hard-won, discovered not in equations on a blackboard, but in the steady arc of a weight in the hands of a patient experimenter. Christian Huygens may not be as widely known as Galileo or Newton, but his pendulum clock ranks among the great inventions of the scientific age. It bridged philosophy and practice, uniting the abstract beauty of motion with the gritty needs of navigation, astronomy, and daily life. And in every swing, it whispered a new idea into human consciousness: that time could be not just observed, but mastered. From cathedral chandeliers to the ticking of a clock in a Dutch workshop, the pendulum had completed its first transformation. It had moved from curiosity to necessity, from observation to regulation. The world would never mark time the same way again. If Galileo and Huygens gave the pendulum its role in history, it was physics that gave it a voice in science. A pendulum is simple to look at, a weight suspended from a string or rod moving back and forth. Yet hidden inside that simple motion is an extraordinary depth of mathematics and insight into the laws of nature. At its core, the pendulum is a conversation between gravity and inertia. When you lift the weight to one side and let it go, gravity pulls it downward. But inertia resists, carrying it past the lowest point. Back and forth it goes, gravity tugging it inward, inertia carrying it outward. Left unchecked, this could continue forever. But in the real world, friction and air resistance steal energy with each swing, and so the motion gradually fades. One of the most celebrated features of the pendulum is the regularity of its period, the time it takes to complete a full swing. Physicists eventually discovered a relationship that links this period primarily to the length of the pendulum and the strength of gravity. Remarkably, the mass of the bob does not matter. Whether you suspend a heavy lead ball or a wooden apple, if the length of the string is the same, the swings will take the same time. This independence from mass is counterintuitive at first. We are used to thinking of heavy things as moving differently from light ones. But the pendulum demonstrates that, under gravity's pull, all objects share the same rhythm. This realization carried immense philosophical weight. For centuries, debates raged about whether nature treated objects differently depending on their heaviness or substance. The pendulum gave a clear answer. Gravity plays no favorites. In the precise counting of its swings, one could see equality written into the fabric of motion. Of course, the regularity of a pendulum is not absolute. For small swings, those gentle arcs Galileo observed in the cathedral, the period is nearly constant. Physicists call this the small angle approximation. Within a few degrees of displacement, the error is tiny, almost invisible to the naked eye. But as the swings grow larger, the time begins to stretch. A wide sweep of 40 or 50 degrees lingers slightly longer than a modest one. To a clockmaker, this difference matters. A cathedral lamp may appear steady, but a precision clock must demand more exacting truth. It was here that Christian Huygens made one of his refinements. By constraining the pendulum's path into a curve known as a cycloid, shaped somewhat like an arch traced by a rolling wheel, he could make the swing more nearly independent of amplitude. Though this solution was complex and rarely used in practice, it reflected the deep attention scientists paid to the subtle ways nature departed from ideal perfection. Then there is damping, the quiet thief of energy. Every real pendulum slows. Air molecules buffet the swinging weight, and friction at the pivot bleeds momentum away. This damping gradually shortens the arcs until the pendulum rests motionless. In clocks, clever mechanisms counteract this loss, giving the pendulum a tiny push each cycle to maintain its motion. Without this assistance, the tick-tock rhythm would soon fall silent. Yet, damping is not always an enemy. In fact, its balance with external force gives rise to one of the most fascinating phenomena in physics: resonance. If you push a pendulum in step with its natural rhythm, not too fast, not too slow, each push adds to its energy, and the swing grows wider and wider. Anyone who has played on a swing set knows this instinctively. Lean back and kick at just the right moment, and the swing soars. Push at the wrong time, and the motion falters. Resonance is not only a playground lesson, it is a principle that governs everything from the shattering of glass by sound to the oscillations of bridges in the wind. The pendulum also offers a gateway to chaos. Attach not just one weight, but two, linking them in series, and you create the double pendulum. At first it may swing in graceful arcs, but soon the motion becomes wild, unpredictable, and astonishingly sensitive to the smallest changes. A fraction of a degree difference in starting angle can lead to an entirely different path. The double pendulum has become a classic classroom demonstration of chaos theory, showing how deterministic laws can produce motion that appears utterly random. From such simple beginnings, the pendulum reveals the richness of complexity hidden in the universe. Beyond demonstrations, pendulums have been tools of precision measurement. They provided one of the earliest reliable ways to measure the strength of gravity itself. By timing the swings of a carefully constructed pendulum, scientists could calculate the value of gravitational acceleration at a location. In the 17th century, the French astronomer Jean Richet noticed that a pendulum clock he carried to Cayenne in South America lost several minutes per day compared to its performance in Paris. The difference was due to gravity being slightly weaker near the equator than at higher latitudes, a result of Earth's rotation causing a bulge at the equator. This observation gave direct evidence of Earth's shape and rotation, supporting Isaac Newton's theory that our planet is not a perfect sphere, but slightly flattened at the poles. In the centuries that followed, pendulums became portable laboratories for testing fundamental physics. Scientists used them to measure the local value of g, mapping variations across the globe that revealed differences in Earth's density and geology. Expeditions carried precision pendulums to remote islands and mountain ranges, their swings providing silent data about the hidden structure beneath the ground. Even into the modern age, pendulums have been used to probe the foundations of physics. Experiments with torsion pendulums, a related device where a mass twists on a wire, have tested the inverse square law of gravity, searching for tiny deviations that might hint at new physics beyond Newton and Einstein. Pendulums have also been used in relativity experiments, checking whether the Earth's rotation, mass distribution, or cosmic influences subtly alter their motion. One of the most delicate pendulum-based experiments was performed by Laurent Eötvös in the late 19th and early 20th centuries. Using torsion balances, essentially horizontal pendulums, he tested whether different materials fall at the same rate in Earth's gravity. His meticulous measurements confirmed the equivalence principle, a cornerstone that would later become central to Albert Einstein's general theory of relativity. In a sense, the gentle twisting of pendulums paved the way to our modern understanding of space-time itself. The pendulum also illustrates how physics connects the human scale to the cosmic. Its period, the time for a full swing, depends on length and gravity. By lengthening the pendulum, one can create swings that take seconds or even minutes. Some giant pendulums, hung in tall buildings or observatories, take half a minute or more to complete their journey. These monumental instruments serve both as demonstrations and as meditations, reminding us that time can be stretched and slowed, yet always remains steady. But there is more than mathematics and measurement in the swing of a pendulum. Watching it, one cannot help but feel a sense of inevitability. The motion is regular, almost hypnotic. It suggests rhythm, order, and the passage of time itself. Each swing is unique, yet each belongs to a pattern. There is poetry in the way such a simple object mirrors the heartbeat of the cosmos. And yet, the pendulum is never perfect. Air drags it, pivots wear down, and the symmetry of nature, yields to tiny imperfections. In this, too, lies a lesson. Physics is not about discovering an unattainable ideal, but about understanding how reality, with all its friction and irregularities, dances around principles. A pendulum is not an abstraction, but a real object in a real world, and its truth emerges from the balance of law and imperfection. Today, pendulums still appear in classrooms and science museums, often as giant installations where visitors marvel at the slow procession of a swinging weight or the intricate dance of multiple pendulums in a wave pattern. They are reminders that profound truths can emerge from the simplest of devices. A ball on a string, given a push, becomes a teacher of gravity, rhythm, resonance, chaos, and even relativity. From Galileo's cathedral lamp to Eötvös versus torsion balance, from the tick of a grandfather clock to the artful installations in modern museums, the pendulum has revealed layer after layer of nature's laws. Its hidden life is not just in history, but in physics itself, where each swing, simple and inevitable, carries the weight of centuries of discovery. By the middle of the 19th century, pendulums had already reshaped human life. They had brought precision to clocks, discipline to cities, and reliability to science. But in 1851, the pendulum would reveal something far larger, not just the order of seconds and minutes, but the turning of the entire Earth. The man behind this revelation was Léon Foucault, a French physicist with a gift for ingenious demonstrations. Foucault was not a professor at a grand university, nor a man with vast mathematical achievements. Instead, he was an experimenter, someone who found clever ways to make invisible truths visible. And in January of 1851, he devised an experiment so simple and so elegant that it became one of the most celebrated demonstrations in the history of science. Foucault's idea was straightforward. If the Earth is rotating beneath our feet, then a pendulum swinging freely should reveal that motion. Imagine suspending a long pendulum and setting it in motion. The pendulum swings back and forth in the same plane, governed only by inertia. But the Earth beneath it is constantly turning. To someone watching from the ground, the path of the pendulum appears to slowly rotate. The effect is subtle, but it is inexorable. On January 3, 1851, Foucault first tested the concept in the cellar of his house in Paris, using an 11-foot pendulum with a small iron bob. The results convinced him. A month later, he presented the experiment publicly at the Paris Observatory, with a pendulum 28 feet long. The slow, steady rotation of the swing was unmistakable. It was as if the Earth itself had betrayed its motion through the pendulum's quiet persistence. But the true triumph came in March of that year, when Foucault was invited to demonstrate his experiment in the Pantheon, the great domed church in Paris that had been transformed into a secular monument. From the center of its vast dome, he suspended a pendulum 67 meters long, more than 200 feet, with a massive lead bob weighing over 60 pounds. Crowds gathered beneath the soaring dome to watch. The pendulum was set swinging, and as minutes passed, the audience saw the line of its motion slowly rotate relative to the floor. Markers placed beneath it were gently toppled one by one as the plane of the swing shifted. Here, at last, was a proof of Earth's rotation that required no telescope, no abstract calculations, no appeal to authority. Anyone could watch and see. The Earth was turning, and the pendulum revealed it. The demonstration was electrifying. In an era still filled with skepticism and debate about scientific claims, Foucault's pendulum offered a direct, almost theatrical confirmation of something that had long been known in theory but never shown so tangibly. The simplicity of it was part of its genius. No complex instruments were needed, no delicate apparatus, just a weight, a string, and time. The truth of Earth's rotation unfolded in plain sight, undeniable. News of the experiment spread quickly. Soon, Foucault pendulums were being constructed across Europe and beyond. They appeared in observatories, universities, and eventually museums, becoming both scientific tools and public attractions. Visitors marveled at their steady swing, their slow and silent rotation. In each case, the message was the same. The ground beneath your feet is not fixed. The planet is moving, and here is the proof, swinging before your eyes. The effect of latitude made the demonstrations even more fascinating. At the North Pole, a Foucault pendulum would complete a full rotation in 24 hours. At the equator, the effect would vanish, with no apparent rotation at all. In between, the rate of rotation varied predictably. Thus, each pendulum became not only a proof of Earth's spin, but also a local measure of one's place on the globe. Standing beneath the dome of the Pantheon, Parisians could see not just the fact of Earth's turning, but their own latitude written in the slow procession of a swinging weight. The spread of these pendulums reflected more than curiosity. They became symbols of science itself, elegant, unanswerable demonstrations that invited the public to witness nature's laws without mediation. In an age of growing museums, world fairs, and public education, the Foucault pendulum became a centerpiece, bridging the gap between the abstract world of physics and the everyday experience of ordinary people. Even today, walk into a science museum almost anywhere in the world, and you are likely to find one, a great pendulum swinging endlessly, its slow rotation marking the invisible turning of the Earth. There is a deep philosophical resonance in this. The pendulum, once a humble servant of clocks, had now revealed a planetary truth. Its swing was local, confined to a dome or a hall. Yet its meaning stretched across the globe, showing that we are passengers on a spinning world. To watch a Foucault pendulum is to experience a quiet shift of perspective, the recognition that the ground beneath us is not absolute, but part of a greater motion. It is perhaps the most poetic of demonstrations, a simple, almost childlike experiment that points directly to cosmic reality. There is no need for complex mathematics, though the physics behind it is rich. The pendulum does not shout, it whispers, and in its whisper it tells us that we are never still, that our lives unfold on a world that spins ceaselessly beneath the stars. For Foucault himself, the pendulum was one of several ingenious experiments. He also invented the gyroscope, another device to reveal Earth's rotation. But it was the pendulum that secured his fame. When he died in 1868, the newspapers remembered him above all as the man who made the Earth turn before people's eyes. To stand before a Foucault pendulum today is to share in that moment of wonder. The weight swings, silent and steady, as if detached from the chaos of the world around it. The markers fall, one by one, as the minutes pass. And you realize that this simple device connects you directly to the scale of the planet itself. No longer are you merely an observer of a swaying weight. You are part of the rotation it reveals, carried along on the spinning Earth. The hidden life of pendulums had, by Foucault's time, already given us mastery over minutes and seconds. Now it gave us something greater, a proof that our home is not fixed, but a moving body in the cosmos, a string, a weight, a swing, and the Earth itself confessed its motion. By the time Foucault's pendulum was swinging in the Pantheon, the device had already proven itself as more than a clock regulator or a planetary witness. Its usefulness extended into new territories, carrying the pendulum from the realm of timekeeping into geology, engineering, and even art. The hidden life of pendulums, it turned out, was not finished with us. One of the most practical new roles for pendulums came in the study of earthquakes. Long before modern seismology developed its sophisticated instruments, scientists realized that a suspended weight responds to the trembling of the ground. If the Earth shakes beneath a hanging mass, the weight tends to remain momentarily in place, while the ground, and the frame holding the pendulum, shifts beneath it. Early seismographs in the 19th century were essentially giant pendulums with pens attached, tracing lines on rotating drums of paper. When the ground quivered, the relative motion between the stationary pendulum and the moving earth produced jagged marks, turning invisible tremors into visible records. These early devices were crude by today's standards, but they established a principle that remains in use. A pendulum is nature's way of detecting imbalance. Its inertia resists sudden changes, making it an ideal witness to motions we cannot otherwise perceive. From those first swinging seismographs, the field of earthquake science grew, eventually mapping tectonic faults, measuring magnitudes, and even providing early warnings. Behind the technological advances lay the same truth Galileo had glimpsed. A pendulum is a faithful servant of physics, always revealing what force has been applied, always honest in its response. Yet not all pendulums swing with such composure. Link one pendulum to another, letting a second weight hang from the first, and the result is the double pendulum, a system famous for its unpredictability. At first, the motion seems orderly, the two arms swaying together in graceful arcs, but soon the second pendulum breaks away into chaotic patterns, darting and twisting in ways that defy prediction. A tiny change in starting angle can produce a wildly different trajectory. The double pendulum has become an icon of chaos theory, a tangible metaphor for the sensitivity of complex systems. In its restless motion, we glimpse the unpredictability of weather, the instability of economies, the fragility of ecosystems. Deterministic laws still govern every swing, but the outcome resists foresight. It is a reminder that even within nature's strict rules, surprises lurk, and the future can be shaped by the smallest of differences. Beyond laboratories, pendulums found a comfortable home in engineering and daily life. The most familiar role, of course, was in clocks, where pendulums served as regulators for centuries. But other uses multiplied. In music, the metronome, essentially a small, adjustable pendulum with a ticking escapement, became an indispensable tool for musicians, enforcing steady tempo in practice halls around the world. To hear the tick of a metronome is to hear the same principle that guided Huygens clocks. A weight, a swing, a rhythm unbending to distraction. Engineers borrowed pendulum principles in less delicate ways as well. The giant swinging arms of amusement park rides, which thrill passengers by lifting them skyward and plunging them back, are pendulums at heart. They rely on the same play between gravity and inertia, only scaled up and paired with steel structures and safety harnesses. To ride one is to feel in your stomach the same physics that Galileo timed with his pulse, exaggerated into spectacle. Even suspension bridges can be thought of as pendulum-like systems, swaying under wind or traffic, their stability depending on mastering the rhythms of oscillation. In the modern era, pendulums have also become instruments of art. One striking example is the phenomenon of pendulum waves. Imagine a row of pendulums, each slightly different in length, all set swinging together. At first, they move in unison, but as the seconds pass, their rhythms drift apart, producing patterns of interference, waves that ripple, form, dissolve, and reappear. To watch a pendulum wave is to see order and disorder play out in elegant choreography. For minutes on end, the pendulums seem to conspire to create shapes, arcs, spirals, cascades, only to break apart and return again. These installations, often seen in museums or performance spaces, blend science and art in mesmerizing ways. They show the audience not just the physics of pendulum motion, but the beauty of rhythm and variation. Each swing is simple. Together they weave complexity. They are living demonstrations of harmony arising from difference, of pattern emerging from the simplest of motions. In all these roles, scientific, practical, artistic, the pendulum reveals its hidden versatility. It can be a delicate sensor of earthquakes, a wild dance of chaos, a steady tick of a metronome, or a sweeping spectacle of moving art. Always the same principle lies beneath: gravity, inertia, rhythm. A weight swings, and the world is revealed. The pendulum, once a tool for proving time and rotation, has become something more, a mirror of nature's diversity. It can embody precision or unpredictability, stability or surprise. Its life reaches far beyond clocks and cathedrals, stretching into the very ways we measure, understand, and experience motion. The pendulum, for all its service to science and measurement, has also swung deeply into the realm of culture and imagination. Beyond the laboratory and the observatory, it has long been a symbol of inevitability, of life and death, of fate's unyielding rhythm. Its steady motion has captured not just the attention of scientists, but the minds of writers, philosophers, mystics, and even psychologists. Perhaps the most famous literary appearance of the pendulum is in Edgar Allan Poe's chilling short story, The Pit and the Pendulum, published in 1842. In it, a prisoner of the Spanish Inquisition awakens to find himself strapped down, a massive pendulum with a razor-sharp blade suspended above him. With each slow swing, the blade descends ever closer, threatening to cut him in half. Poe exploits the pendulum's regularity, its implacable back and forth, to build unbearable tension. The story is not just about physical danger, but about inevitability, the slow approach of death that no effort can stop. In Poe's hands, the pendulum becomes more than a machine. It is time itself, sharpened into terror. This association with inevitability has echoed throughout culture. A pendulum swings with a calm certainty. Each return feels fated, each passage through the center unavoidable. It has often been invoked as a metaphor for history or politics, the pendulum swing of ideas and power, moving from one extreme to another before inevitably reversing course. The metaphor captures both change and continuity. Progress may move forward, but always it seems to return, as if history itself were tethered to gravity. In philosophy, the pendulum has served as a symbol of life's rhythm. It is relentless, yet also strangely comforting. The tick-tock of a clock's pendulum is like a heartbeat for a household, a reminder that time moves steadily on. For some, this rhythm suggests mortality, the steady march toward an ending. For others, it embodies balance, the oscillation between activity and rest, effort and ease, sorrow and joy. To watch a pendulum is to be reminded of cycles, the rise and fall of civilizations, the swing of moods, the alternating currents of human experience. Beyond metaphor, pendulums have also found a place in mystical traditions. For centuries, some have used pendulums as tools of divination or dowsing. Held in the hand, a small weight on a string is allowed to swing freely, its motion interpreted as answers to questions. In water dowsing, practitioners claimed the pendulum would reveal hidden springs or minerals underground. In spiritualist circles, pendulum dowsing has been used to communicate with unseen forces, the slight unconscious movements of the hand amplified into meaningful swings. Science, of course, has offered skepticism. The movements of a handheld pendulum can often be explained by the ideomotor effect, where small, unconscious muscle movements create motion without the person realizing it. What seems like supernatural guidance is more often the body's own subtle tremors. Yet, the popularity of pendulum dowsing persists, perhaps because it resonates with our desire for hidden knowledge, for a direct and personal link to truths beyond our reach. The pendulum has also entered psychology, most famously through hypnosis. For much of the 19th and 20th centuries, images of hypnotists often showed them holding a swinging pocket watch or pendulum before their subjects' eyes. The idea was simple. The steady, repetitive motion could lull the mind, focusing attention until the subject became susceptible to suggestion. In reality, hypnosis is a far more complex state of focused awareness, and modern practitioners rarely use literal pendulums. But the cultural image endures, the pendulum as an emblem of trance, of slipping into altered states of consciousness. Its steady rhythm seems naturally suited to drawing the mind inward, quieting distractions with repetition. These cultural uses remind us that the pendulum is more than a scientific instrument. It lives in the imagination as well. It is a blade in Poe's dungeon, a metaphor for history's swings, a tool of mystics, a symbol of hypnosis. Its motion, so simple and so inevitable, lends itself to meanings beyond physics. It becomes a canvas for our deepest fears, our hopes for balance, our fascination with rhythm and inevitability. In the end, perhaps this is the pendulum's greatest hidden life, not just as a weight on a string, but as an idea swinging endlessly between science and symbolism, between the measurable and the mysterious. Even in our age of lasers, satellites, and atomic clocks, the pendulum still swings in classrooms and science halls across the world. Walk into almost any science museum, and you may find a Foucault pendulum suspended from the ceiling, its heavy bob gliding silently over the floor, toppling markers one by one. Children gather around, wide-eyed, as guides explain that what they are watching is proof of Earth's turning beneath their feet. In that moment, a truth larger than themselves becomes tangible. In classrooms, too, pendulums remain trusted companions. Physics students time their swings with stopwatches, measuring the way length dictates period, testing the constancy that Galileo first noticed centuries ago. Teachers still use pendulums because they are both simple and profound. They require no advanced technology, yet they open doors to fundamental principles of motion, gravity, and rhythm. A string, a weight, and patience. That is all it takes to step into the heart of physics. There is something enduring in this simplicity. The pendulum teaches not only science, but perspective. It reminds us that discovery does not always come from complex machinery, but often from close attention to the ordinary. Galileo needed only his pulse and a lamp. Huygens needed only a workshop and a vision of accuracy. Foucault needed only a dome and a swinging weight to reveal Earth's spin. From cathedral ceilings to clockmakers' benches, from seismographs to chaotic art installations, the pendulum has been our quiet partner in exploration. It has measured the pull of gravity, steadied our clocks, revealed the turning of the Earth, and even slipped into our literature and imagination. Perhaps that is why it continues to fascinate us. The pendulum swings at the intersection of the simple and the profound. It is a humble object, a weight on a string, yet it holds within it a history of science, a philosophy of balance, and a poetry of inevitability. As long as it swings, it will invite us to wonder about time, about motion, and about the hidden truths that live in plain sight.